Hi everyone, and welcome back to week 8. Believe it or not, we're at the halfway point in the semester now. And the topic for today's lecture is going to be sampling and sampling distributions. First, I want to talk a little bit about inferential statistics. So I left off that last unit that we had saying that when you're looking at what's in front of you in your sample or population and describing it, you have descriptive statistics. Inferential statistics have a different goal. So descriptive statistics, as I said, describe a sample or population that you have in front of you. And descriptive statistics include things like the mean and the standard deviation and proportions. Anything that tells you about the data that you are looking at directly. Inferential statistics is all about using data to try to learn about a broader population that you can't see. And specifically, we're going to use what we call a representative probability sample, which we'll meet in a minute, to make a generalization about a population. In other words, with inferential statistics, you're going to use a small sample or group drawn from a population to learn more about that population broadly. And we're going to be focusing on inferential statistics for the whole rest of the class. There are two types of inferential statistics that we're going to get to know. One are confidence intervals, and one are hypothesis tests. But before I talk about that, which is all kind of weeks away, we're going to talk about some of what you need to know in order to do inferential statistics. We're going to start with sampling. Sampling refers to pulling out members from a broader population and collecting them into the group that's your sample. And we talked about sampling earlier in the semester. Right now, though, I want to talk about a specific kind of sample, which is a simple random sample. The simple random sample is considered the gold standard of sampling. It's the best kind of sample you can have. And the reason for this is that a simple random sample is always going to be representative, meaning that it's always going to be similar to the population. But more on that in a second. What a simple random sample is a sample in which every member of a population has an equal chance of being selected into that sample. So whatever your population is, every member of that population has an equal chance of becoming a member of the sample. In other words, who gets selected into the sample is completely random. And there are two steps to taking a simple random sample. The first is to list every member of a population. And so whatever population it is that you're interested in, you have to have some list of every member that's in it. The next step is to use some random process to select elements from that list. So whatever list you have, you're going to use some sort of random process to select elements. So a random process could be something like a random number generator, or it could mean literally, pulling something out of a hat. And examples of simple random samples are the samples that you get for jury selection. And typically these are random samples based off of registered voters. So they start with a list of registered voters, and then they use some sort of random number device to select people off that list. So everybody on the list has an equal chance of being selected into the sample. The Powerball Lotto. There's a big thing full of balls, and balls fall out randomly. And that's your random sample of numbered balls. So bingo is the same idea. So you have your total population is all the balls with the different numbers on them. And then the random process is the big thingamajig that makes them come out for the Powerball. And then one final form of simple random sampling is literally just picking things out of a hat. So you might remember my basket full of superheroes here, and I can take a simple random sample of superheroes. So I'll just have them all in here. That's my population, and I'm going to take a sample of 3 superheroes. Wiggle my fingers around. I got a falcon. Wiggle my fingers around. I got another falcon. Wiggle my fingers around. And I got a Captain America. So I took a random sample out of this hat. So I had all the superheroes in here. That's equivalent to having them all listed out, right? I just have my total set of superheroes. And then I'm using a random process, which is grabbing out of the basket to select superheroes out of my set of superheroes. So that's also an example of a simple random sample. And in this class, we're going to assume that all samples are simple random samples. In reality, this is very rarely the case. Simple random samples show up every once in a while, but for the purposes of what we're doing here, we're going to assume that any sample we talk about is a simple random sample. And as I said before, simple random samples are important because they're representative. What this means is that the characteristics of the sample, in other words, your sample statistics, are going to tend to resemble the characteristics of the population. In other words, the population parameters. So when you take a simple random sample, you can assume that the characteristics of that sample are going to be similar to the characteristics of the population you took it from. Which means that you can expect to find similar proportions, similar means, similar standard deviations, and similar everything else. So when you take a simple random sample, it just becomes sort of a mini version of that population you're looking at, and you can expect everything to be pretty close to the population you drew it from. One thing to be on the lookout for, though, before we get back into what we're doing in this class, are statistics based on non-representative samples. And this is something that you see all the time when statistics get reported in the news or whatever. If the sample isn't representative or otherwise close to it, the statistics can be really off. And so one example I want to give you is this question of whether you favor or oppose the death penalty for persons convicted of murder. And you might remember I asked you this question at the beginning of the semester in the class survey. In our class, 28.3% of the class are in favor of the death penalty and 71.7% of the class oppose the death penalty. So if you just stopped there and said, this is my sample, therefore I know that people tend to oppose the death penalty more than favor the death penalty, you'd have a problem. And that problem is that students in this class are not a representative sample of people in general. And if you look at a probability sample of the US population, you get a completely different story. And I think this data is from 2018, but be about the same now, where 63% of the US population favors the death penalty and 36.8% oppose it. So it's totally flipped. And what's going on here is that Rutgers data analysis students are not representative of the US population. And for one thing, you guys tend to be younger, you tend to be more educated on average since you're all in college. You tend to be a whole bunch of other things, that don't exactly match the US population. So your attitudes don't necessarily match the US population either. So when trying to make inferences about a population, it's really, really important to know that your sample is going to be representative of that population. With samples, though, comes something called sampling error. And sampling error refers to the idea that even when you take a probability sample, the best sample in the world, you end up with differences between the sample and the population that it came from just by chance. And one thing that is true is that samples that are larger tend to have less sampling error. In other words, the bigger your sample, the more likely it is to resemble the population on all the different statistics that we talked about. So if we think about a coin toss again, if you toss a coin 10 times, you'd expect it to come up as heads 5 of those times, right? Because it's a 50-50 chance. But you wouldn't be surprised if you happen to get 6 heads. So thinking of that in terms of a sample, if you had a sample of 10 and you were expecting to get 5 of something, it wouldn't be surprising if you just happened to get 6 by chance. So samples are always drawn from a random process. This means that there's random chance involved. And what this means is that the characteristics of a sample often differ from the characteristics of a population in small ways just by chance. But the bigger your sample, the less likely it is that your sample is going to be really far off. So let's say you tossed a coin 10,000 times. You'd expect to get 5,000 heads, right? Still a 50-50 chance. And in this case, you'd expect to get 5,000 heads, but if you got 6,000 heads out of those 10,000 coin flips, just behind my head, you should be pretty surprised. And the idea here is that in the first example, you only needed to get 1 extra heads to get up to 6 heads. But if you're tossing a coin 10,000 times, you need to get 1,000 extra heads in order to get up to 6,000 heads. And this illustrates a sort of rule of reality, which is that unlikely events tend to even out if you repeat a process again and again and again. This is something called the law of large numbers. The more times you repeat some sort of probabilistic event, the more likely you're going to get at that underlying probability distribution, which is going to be based off a population. So when you're sampling from a population, just to recap, you could often see small differences between your sample and your population. But it's unlikely that your sample is going to be very different from your population. And the bigger your sample is, the more similar it's likely to be to that population. And here's why this matters. Because of sampling error, when you take a sample, you can't assume that the sample and the population are exactly the same. This means that a sample can give you a best guess only about what's actually going on in the population itself. And for this next example, I'm going to come back to the problem that we actually had on the last problem set. So in that, I gave you guys a probability distribution for the different types of cases that a defense attorney was getting in a given week. So we're going to use type of case that a defense attorney gets as a variable here. But let's ignore what we said on the problem set and just say that if you sample 100 cases, so you look at 100 cases that a defense attorney gets, you might find that 25 of those are drug cases. This is your sample. This is the only thing you know. You know that in this 100 cases that you looked at, 25 of them are drug cases. And you're trying to use this to guess at what's going on in the population. Based on your sample, the best guess that you can make is that 25% of cases out there are drug cases, because 25% of the cases in your sample are drug cases. The problem is that because samples often differ from populations, you can never be sure that that 25% is exactly right. So it's possible that the population's different, maybe it has 30% of drug cases, and you just happen to get fewer drug cases in your sample of 100 cases. But just looking at that sample, you have absolutely no way to be sure because you can't see the whole population. But what we can do, and what we're going to talk about how to do in this class, is how to take that sampling error into account in order to get an idea about how accurate our best guess is. And what we'll learn how to create down the line is essentially a buffer around the best guess that tells you what you can expect realistically from the population. In order to get there, though, we're going to have to learn a little bit about something called probability theory. And probability theory is based around the idea of what happens when you take multiple samples. I'm going to demonstrate taking multiple samples using some very important information about all of you, which is the number of letters in your first name, as it's written on the roster. So what I have here is an example of a population. And this population are people in this class, and then I have a variable as well. The variable is the number of letters in your first name as it is typed into the roster. And I'm going to look at a statistic for this variable. The statistic is going to be the mean number of letters in people's first names in this class. So again, we're thinking of this as a population. And so it'd be more accurate to call it a population parameter. So the population parameter that we're interested in is the mean number of letters in everybody's first name. So the population mean, if you actually go through and you take the mean for all of these, is 6.51. So on average, the number of letters in the name of somebody in this class is 6.51 letters. Also, I'm sorry for the 3 people who are beneath my head. I didn't think about that when I made the slide. So we have this population here where we have the population as our class, and the variable that we're interested in is this number of letters in a first name. Now we're going to see what happens when we take a sample. And here we're going to take a sample of 5 names out of the 49 people in this class. And on this slide, I have highlighted 5 names that came up when I took this sample. The mean number of letters in these 5 people's names was 8.4. So that's a little bit different, right? And you could imagine that if I didn't know what was going on in the population, and I only took a sample of these 5 people, I would assume that there's about 8.4 letters in an average name in this class, which would be a bit off. And as a side note here, in order to take these samples, I actually used a random number generator online and highlighted everybody's name in a spreadsheet and then found the average number of letters in your guys' names. If you're wondering, I do have better things to do with my time, but that's what I did instead. And in order to demonstrate what happens when you take multiple samples, I'm actually going to go through this process 10 more times. So yeah, when I say I had better things to do, I can promise you I probably had better things to do. But I actually did this 10 more times, and I'm going to show you what happens in each of those different times. So again, going into this, remember the whole class is the population. We have a population parameter, which is a mean of 6.51, and we're going to look at the sample means that we get when we take different samples out of this class. So our first sample here had a mean of 8.4 letters. We're going to see what happens in the next 10 samples that I take. 6.2 letters. 6.2 letters again. 6.4 letters. 7.2 letters. 6.4 letters. 6.6 letters. 6.4 letters. 6.0 letters. And again, each of these is a sample of 5 names where I took the mean number of letters in those 5 names that I randomly sampled out of the population of students in this class. 7.2 letters and 5.8 letters. So those are 10 more samples drawn from this class. And what we should have noticed as we went along is that for the most part, the letters were pretty close to that population mean of 6.5, but they did vary. Some were higher and some were lower. So let's sum up here what happened in this last example that I just had. The actual mean for the class, so the population mean, was 6.51 letters. In the first sample that we took, we had a mean of 8.4 letters, which is pretty far off. Here are the next 10 sample means. And as you can see, most of them are pretty close to 6.5, which is the actual class mean, but some of them are different. So what we're seeing here is the variation in sample statistics that you get when you compare them to a population parameter. And for the most part, they're pretty close because you would expect a randomly drawn sample to be pretty close to the population parameter, but some of them get to be a bit different. But watch what happens when I do this. If I take the mean of those 10 sample means that I have in that table, I get an overall mean of 6.44. In other words, I took the mean of 6.2, 6.2, 6.4, 7.2, 6.4, 6.6, 6.4, 6.0, 7.2, and 5.8. I took the mean of those numbers, which were all the sample means, and then I got 6.44. And what's cool here is that it's really, really close to the actual mean. And in fact, we are less than 0.1 letters off. And what's even cooler is that this is a really fundamental property of sampling, which is that if you take a whole bunch of samples, calculate some statistic like the mean, and then find the average of that statistic, it's always going to resemble the population parameter that it came from. And I can tell you I've done this in this class for several years now, and it always happens exactly the same way. You get some variation in the sample means because they just happen to be different by chance, but then when you put them all together, you get a number that's really, really close to the actual mean. And if you're wondering, with that first sample mean, that was 8.4, which is just bigger than all the rest, if you include that in the average, it comes up to 6.6. So even with that one out there that might be considered an outlier, you still have a mean of means that's really close to the actual original. You can also see a graph here, or half of a graph, that shows the distribution of these sample means. So I'm going to post that up somewhere else. Whoops. And what this graph shows, that again you'll be able to see, not in the video, is the distribution of sample means. And you can see that they're pretty nicely distributed around that 6.5. So most of them are pretty close. The tallest bar is the bar that includes 6.5, and the further away you get, the fewer sample means you have out there. So that's the sample means for the 10 that are in the table. And so with all of this, I want to bring you guys to the idea of something called a sampling distribution. And a sampling distribution is going to be similar to concepts we've had before, especially the probability distribution. But what a sampling distribution tells you is all possible values of some sample statistic, such as a sample mean, and the probability of getting each one. So as we just saw, if you take a sample, you can get a different value for some statistic between different times you take the sample. So the mean number of letters, you can get a whole bunch of different means. So our sampling distribution is going to list out all possible values of that sample statistic you're interested in, but then we'll also see the probability of getting each one. And sampling distributions can have many shapes based on the underlying population. So these are some examples of sampling distributions that you might see. And what you have on the x-axis for all of them is some sample statistic. In this case, the sample statistic is a mean. And the higher your line on the probability distribution, the more likely it is. So in the first one, it's a triangle upside down, and the point is the most likely sample mean. And then where the line gets lower, you have unlikely sample means. Same thing with the one in the middle, it's sort of a skewed distribution. You have likely sample means at whatever value has the highest peak, and then the further away you get, the less likely they are. So it's really, really similar to reading a probability distribution in a graphical form, except instead of looking at individual values that you might get, you're looking at statistics like a sample mean. Also, side note, we have hit the point in the semester where in the spring we went remote. So I have some of these pictures from my notes from there that might be popping up in the lectures as well. Sampling distributions are useful. And they're really, really useful because of something called the central limit theorem. And what the central limit theorem says is that even though sampling distributions can have different shapes, they're always normally distributed under two different conditions. One is when the underlying variable itself is normally distributed. So if you have a variable that can be described with a normal distribution, your sampling distribution is going to be normally distributed as well. But if you have a variable that's not normally distributed, your sampling distribution is going to become a normal distribution as long as the sample size is greater than 30. This means that no matter what your variable looks like, if you're looking at sample means, you can assume that the sampling distribution for them is normally distributed as long as your sample is greater than 30. And so I'm going to talk about this more specifically with the sampling distribution for means. So if we're thinking about the mean as our statistic of interest, just like we had in the demonstration with the names, we're going to say that the sampling distribution for means is going to be normal, meaning that it has all the characteristics of a regular normal distribution. It's bell-shaped. This means that there's some mean value that's going to be the most likely, and then the farther away you get out from that mean value, the less likely they are. So with the names, it was more likely to get a value in the middle, less likely to get a very low mean, less likely to get a very high mean. So a sampling distribution for means under either of those conditions is always going to have that be the case, where there's going to be a central value that's the most likely, and then the further away you get, the less likely it will be. The sampling distribution for means also has a mean and a standard deviation, just like any other normal distribution. And here, and when talking about sampling distributions in general, we refer to the mean and standard deviations as mu and sigma like we did before, but we also say what the statistic is that we're sampling for with that subscript there. So we'd say that as mu x bar, and that means that it's going to be your mean, your overall mean of sample means. And your standard deviation would be sigma x bar, and that's going to be the standard deviation of the sample means. And by the way, I'm going to go through all of this in examples in the document camera as well. This is just an overview of what you can expect there. So just like any other normal distribution, if you have a normally distributed sampling distribution, the area under the curve equals the probability. This means that everything we did last week, we can do this week too. It'll just be for sample statistics instead of individual outcomes or values. The 68, 95, 99, 7 rule, aka the empirical rule, also applies here. So when you have a normally distributed sampling distribution, you know what proportion of the area falls within 1, 2, and 3 standard deviations of the mean. And you can also calculate z-scores and use the z-table in the exact same way. So overall, a sampling distribution for means that's based on either a normal variable or a sample that's greater than 30 is going to have all the same characteristics of a regular normal distribution. The one difference here that I'd like to highlight is that the standard deviation in a sampling distribution is referred to as a standard error. So as I move on, I'm going to start referring to it as a standard error, but it means exactly the same thing as standard deviation. It's just a standard deviation for a sampling distribution. And another picture that's covered by my head that I'm going to put somewhere else after this lecture is a picture of a normal distribution that's a sampling distribution. But I'm not going to talk through it right now because you can't see it, and I've talked way too much on this slide to start over from the beginning, so we're just going to come back to that when I start drawing in the document camera. But before I do that, I just want to talk a little bit more about the mean and standard error for a normally distributed sampling distribution. And in looking at sampling distributions, we'll be able to say that the mean for the sampling distribution and the standard error for the sampling distribution are based on the probability distribution for whatever the underlying variable is. And specifically, whatever your variable is, the mean of the sampling distribution is going to be equal to the mean for that variable. For the standard error, which again is the standard deviation of your sampling distribution, you're going to be able to calculate that standard error using something called the standard error formula. I'm going to show you what that looks like in just a minute. Before I do that, I just want to note that larger samples give you a smaller standard error. And the reason for this is that larger samples just tend to have less variation based on random chance, so everything tends to be a little bit closer to the mean. And we'll see what that looks like graphically as well. But otherwise, you can use a normal sampling distribution, so a sampling distribution that's shaped like a normal distribution, exactly like you would a regular normal distribution. So all the things we did last week, you'll be able to do again this week for a sampling distribution. The only difference is that instead of looking at the probabilities of getting different individual values, we'll be looking at the probabilities of getting sample statistics, like the sample mean. And with that, I'm going to go over to the document camera And I'm going to describe some of this with examples and then show you some of what you can do with one of these sampling distributions. That'll be similar to what we did last week.